Okay guys, let's continue on with some solving linear systems. Yesterday we solved linear systems by graphing. So we took a look at graphing two lines to find out where they intersect, and we read off the point of intersection as the solution to the system of the equations, the two lines that we were given. What we found probably straight away was that we had to really make sure that we were spending the time to rearrange both of the equations to get them into slope y-intercept form. We had to really scale both of our axes to make sure that we could actually read the point of intersection off, that it was actually scaled onto our set of axes. And the other thing is that we are really limited to the answer for the point of intersection that we can get, because we're not going to be able to accurately read off a decimal or a fraction answer between those two lines from a graph. It's going to be really difficult to read off anything other than a nice, easy point of intersection. So it's not very accurate, and that's where we want to kind of address today. So there's two methods that we can use to solve linear systems that mean we don't have to graph at all. We can actually just use algebra. So we're going to use two algebraic methods to solve linear systems. One's called substitution and one's called elimination, and today we're going to look at substitution. So what I want to think about is this. So we're going to start right here. This is an exact question you could have been given yesterday. Could have asked you to solve this system of equations. Remember, it just means you have two lines. But we're not going to graph them at all. We're going to solve this system using substitution. So here's what we want to think about. Keep in mind what it is we're doing. We have two equations. This is just one line. This is just another line. And our whole point here, remember what your goal is? Because we don't want to memorize these steps. You're going to see these steps. They're written out in the actual note for you, so you can always copy them down, and we do want you to keep saying the steps in your head for yourself so you understand like where your process is going. But remember what your goal is here, because it will help you not memorize it but really understand it. You want to find out an XY coordinate. Where do these two lines intersect, at which point? So if we can keep in mind that we need an X and a Y coordinate that goes together, and that's going to be the point that's on both of those lines where they meet, it's going to help us work through the algebra. So let's take a look at that. So the first step of substitution says that we need to isolate one of the variables in one of the equations. So step one, when you look at your note, it's going to say that. It's going to say isolate one variable in one of the equations. And it doesn't matter if you have X by itself or if you have Y by itself. We'll look at an example later where we're going to try to make some decisions for that. But you can isolate any variable that you want in either equation. It doesn't matter what, as long as you have one variable isolated in one of the equations. Now, this one was given to us like this. And in this case, we already have a variable isolated in both. So step one's actually done for us. Step two then, and this is where the whole key to the name of the method comes in. Step two says, well, since I know that X is equal to negative 2y plus 3, and I know that X is equal to 3y minus 7, look what I can do. I'm just going to rewrite the second equation. So I'm just going to write X is equal to 3y minus 7, right? That's just the second equation. But I know that X is equal to negative 2y plus 3. The first equation tells me that X is equal to negative 2y plus 3. So look what I can do. I can take the expression that X is equal to, and I can literally just sub it in the place of X in the second equation. Because I have what X is equal to, I can just take it and place it right in the place for X in the second equation. So instead of writing X, I'm going to substitute in what X is equal to. So I took the expression for X and I substituted it right in for X in the second equation. Because look what that gives me. That gives me one equation with one variable that I can easily solve. Because our problem with solving two equations is that they have two variables. The whole point of solving this system is that I need an X and a Y. But right off the bat, I have two equations with two unknowns. Well, the only way for me to solve that is try to apply some kind of algebra, because look what I have here, one equation with just one variable. Well, how do I solve this? That's a really simple, easy algebra equation where now I can just bring all of my y's to one side, all of my numbers to the other side, and I can solve through. So let's go ahead and do that. So we'll see what happens. I'm going to bring my 3y over here, so I'm going to have to subtract it. I already had negative 2y here, and I'm going to have to subtract my 3y from both sides. On this side, I already had a negative 7, and I'm going to bring my 3 over here to be with my numbers, so I have to subtract 3 from both sides. And now I'm just going to collect everything up. So negative 2y minus 3y is negative 5y, negative 7 minus 3 is negative 10. I'm going to have to divide through by negative 5, and we get that y is equal to 2. This is where we want to keep in mind what it is we're looking for, though. So we've done all this algebra and we've solved. Well, what have we found? Well, we've actually found that our point of intersection is 2 for the y coordinate. We're halfway there. We know without graphing, without doing anything else, that looking at the algebra, y is going to be 2 at the point where those two lines intersect. So we need to find the x that goes with it. We need a full point of intersection, but we already know half of the point of intersection. So just like any other time that you know half of a point, we're just going to sub that value in to find the other one. So we're going to do exactly that. We are going to sub y equals 2, because we already got that answer, and you can sub y equals 2 into either of the equations. So you'll see step 4 says take your answer, take half of your point of intersection, sub it back into this equation or this equation, it doesn't matter which one, to solve for your other variable. So I'm going to sub this one into equation number 1. Doesn't matter which one you do, you'll get the same answer. Equation number 1 is x is equal to negative 2 times y plus 3. But now I know that y is 2, so I just sub it right in. And we're going to get negative 4 plus 3. And we can see that x is negative 1. X is negative 1, y is 2. The point negative 1 and 2 is the point of intersection for those two lines. We've solved it using substitution. So again, get one of the variables isolated. If you can isolate one of the variables, you can just take the expression for what that variable is equal to and plop it right in that spot for that variable in the second equation. That's always going to leave you with just one equation that you can solve through. You'll take what that known variable is now, sub it into either equation to find out your other missing part, and the two of those parts together are going to make up that POI, the point of intersection where those two lines are actually going to meet. And we've done it using algebra. You didn't have to graph it all. So let's try another one. Let's let that kind of sink in. We'll keep saying the steps out loud. See what happens if we look at another example. So let's look at B. B says y equals 2x plus 1, and then x plus y is equal to 7. So again, two equations. Keep in mind what it is that you are looking for. A solution to a linear system, when it asks you to solve this, this needs to be your answer. You need to look for an xy coordinate. So you're looking for the point where those two lines intersect, but we're going to do it without graphing. So again, step 1 in linear systems says take one of the variables in one of the equations and make sure you have it isolated. So you need to make sure that you either have x is equal to everything else or y is equal to everything else. But they gave it to us like this. They said y is equal to 2x plus 1. So y is already isolated for us. We already have y by itself. So we're in good shape for step 1. Step 1 is already done for us, so that's good. So then step 2, let's keep going. Step 2 says, well, since I know what y is equal to 2x plus 1, I'm going to go and substitute it in the place for y in the second equation. So let's see what that looks like. I'm just going to rewrite out the second equation. X plus y is equal to 7 was the second equation that they gave us. But I know that I know what y is. I know y is 2x plus 1. Y is equal to 2x plus 1 was given to me. So since I know what y is, I'm just going to substitute out y. I'm not going to write y. I'm going to write what y is equal to. I'm going to substitute it right out and put in 2x plus 1 because that's what y is equal to. And then look what I have. I'm in really good shape. X plus 2x plus 1 is equal to 7. Well, now I can just combine up my like terms here. I have 3x plus 1 is equal to 7. I'm going to have to scoop my 1 over here and subtract it so that 3x is equal to 7 minus 1. 3x is equal to 6. And we can divide both sides by 3. And we get x is equal to 2. X is equal to 2. And again, keep in mind what you've just found. You're halfway there. You have found the x-coordinate of the point of intersection. You found x was equal to 2, so we are halfway there to find that point of intersection. All we need to do is take what we know, sub it back into one of the equations to find out the one we don't know. So let's do that. Let's sub x equals 2 into, and you can sub it into any equation you want. I'm going to sub it into equation number 1. So equation number 1 is y equals 2x plus 1. But I know that x is 2, so it's going to be 2 times 2 plus 1, which means y is going to be equal to 5. There it goes with its partner 2. It's 2 and 5. This point of intersection is where those two lines are actually going to meet. This is the point of intersection of these two lines found using just algebra. That's called the substitution method. So let's try another one. We're going to try to let this sink in, see some examples along the way. So let's look at C. So C gives us 2x plus 5y is equal to negative 18, and x plus 2y is equal to negative 6. So let's go through our steps again and just think out organizing ourselves. We are on our path to find our point of intersection. So step 1 says, get one of the variables isolated in one of the equations. So x either has to be by itself, so you can take what x is equal to and plop it in, or y has to be by itself, so you can take what y is equal to and place that right in the spot in the other equation. But one of the variables has to be by itself. So what you need to do is really ask yourself which of these variables is going to be easiest to isolate. So you want to think about the one that's kind of wrapped up the least. Which of these is the freest to get by itself? If we take a look at all of them, if we just start up here, right now this x is being multiplied by 2 and it's getting a 5y added to it. So to get this x by itself, we'd have to subtract the 5y and divide by 2. That's a lot of stuff going on. To get this y by itself, I'd have to subtract 2x and divide by 5. Again, that's a lot of stuff going on. To get this y by itself, I'd have to subtract that x and divide by 2. Think about the number of operations you would have to do to unwrap to get that x or the y by itself. So right now we can see this x right here is the one that's easiest for us to get by itself. This is the one that has the least number of operations happening to it. It's like the least complicated, the most freest to us right now. So let's try number 2, equation number 2. Let's get this x by itself. So all I'm going to do is rearrange equation number 2 to get x isolated. So I'm going to leave x where it is, and I'm going to scoop my 2y over. So I'm going to need to subtract 2y from both sides, and I get this. So this is still equation number 2. I haven't really done any math here. I haven't done anything other than get x by itself. So I've got an x by itself. X is isolated here. And now I can go ahead and do my substitution, because look what my substitution tells me to do. It says get one of the variables by itself in one of the equations, and we did. We isolated for x. Then it says take this expression for x and substitute it right in x's spot in the first equation, in the other equation. So look what I'm going to do, just like we did before. I'm going to write out 2 times x plus 5y is equal to negative 18. I'm just writing out equation number 1. But now I know that x is negative 2y minus 6, so I'm going to substitute it right in the spot for x. I am going to take out the x. I'm going to substitute in what x is equal to, which is negative 2y minus 6. Substitution. So instead of writing x, I wrote what x is equal to. I substituted out the expression for x. So now I have one equation with one unknown. Takes a little bit of work for us to get here because we have a bracket in here, but that's okay. It just means that we're going to have to distribute that 2 into the bracket. So now we have negative 4y minus 12 plus 5y is equal to negative 18. And I can combine up my y's. I have negative 4y and 5y, which leaves me with just 1y, so that's good. And negative 18, I'm going to have to bring my 12 over. I'm going to have to add 12 to both sides. And I'm going to get that y is equal to negative 6. So look, again, we're halfway there. Negative 6 is the y coordinate in our point of intersection. So let's finish this off. Now we are starting to get what it is we're looking for. We need to find out the partner that goes with y. That means that we need to sub what we know y is into either of the equations. And you can sub it in here, you can sub it in here, you can sub it into this one you've already rearranged. I'm going to sub it into here because x is already isolated, but keep in mind you'll get the same answer no matter where you sub it in. So I'm going to sub y equals negative 6 into, I'm going to sub that into equation number 2. So equation number 2 was x is equal to negative 2y minus 6, but I know what y was. It's negative 6, which means negative 2 times negative 6 is 12. Take that 6 away. X is positive 6. X is positive 6, y is negative 6. Together, they are the point of intersection. That's the solution to this linear system. This is the point where those two lines are going to intersect. And you've done it using just algebra. That's the substitution method. Okay, let's do one last one. So this is a lot going on, but seeing one last one is really going to drive home how useful this method is, but how in the beginning it's going to take a little bit of decision making to make sure that we're being able to carry it through. So I'll show you what I mean. This is our last example. So 2 equations, 2 lines. We have line number 1, line number 2. We want to figure out where do these lines intersect. So we're thinking about what it is we want in the end. Okay, here's the thing. Step 1, we've been saying this all along, is to get one of the variables by themselves. So one variable has to be isolated so you can take what it's equal to, plop it in for its expression in the other equation. That's the whole key to substitution. But in this one that we were given, both were already isolated for us. In this one was already isolated for us. Y was already by itself. In this previous example that we did right here, we kind of went through which one was easiest to get by itself, and we saw that X was the one that was like the freest to get by itself. It had the least number of operations happening to it. But look what happens here, and this is why we really want to kind of go over this one and think about the decision making we have to do. Now I need to decide, should I get this X by itself? Should I get that Y by itself? Should I isolate this X? Should I isolate that Y? I have some decisions to make here. And what I want to do is just kind of flush out why we're going to make that decision. So I'm going to show you what I mean. I'm just going to rewrite this here where you can see it a little bit better. So 6x minus 3y and 4x minus 3y is equal to 5. Okay, so I just want to show you something here and then we'll go back to the actual example. Because what we're going to have to do when we make this decision is this. We're going to have to decide which of these variables is easiest for us to get by itself. So we really need to kind of put some thought into this ahead of time. I'm going to do it for you here and kind of really quickly go through it, but just to really show our thinking so we can actually see why. If I started with this equation and I said I wanted to get this x by itself, look what that's going to look like. I'm going to leave 4x where it is. I'm going to have 5 plus 3y. Then I'm going to have to divide everybody by 4 because my goal is to get one of the variables by itself, which means I'm going to have that. If I try to solve this equation for x and get x in terms of y, if I isolate x, I'm going to have this. That's going to be a messier expression to try to substitute into the other equation. I don't really want to have all these fractions. What about if I try to get y by itself in this equation? If I try to isolate y, I'm going to have to leave y where it is, so negative 3y. I'm going to have to subtract 4x. The 5's already there. Then I'm going to have to divide everybody by negative 3. Then I'm going to have y, which is what I want, y by itself. But then I'm going to have y is equal to 4 over 3x minus 5 over 3. This would be the expression I would need to substitute into the other equation. I don't really want to carry through those fractions. You'll get the right answer, but it might not be the best decision for us to isolate either x or y in this equation. What if we go over here and now we try to substitute, or we try to isolate x in here? What if I try to isolate x here? I'm going to leave x where it is, so I'm going to have 9 now plus 3y over here is equal to 6x. Then I'm going to divide everybody by 6 to get x by itself. So I'm going to have 9 over 6, so I'm going to have 3 over 2 plus 1 over 2y is equal to x. That's also giving me a lot of fractions that in order to carry on with this x and substitute it into the other spot, I'm going to have some fractions in there. You'll get the right answer, but it's maybe not the best decision in terms of which one to isolate. But look what happens if I try to isolate y. If I try to isolate y in this case, I get 9 minus 6x is equal to negative 3y. And now when I divide this by negative 3, by negative 3, by negative 3, I get negative 3 plus 2x is equal to y. Well, now I have a nice easy equation that I can substitute this negative 3 plus 2x in for y in the other equation. So when you're looking through, you really want to kind of go through in your head, and you don't have to do all of this work, obviously. I just wanted to do it so I can show you. Try to think about what you're going to have to do. If I'm isolating this, I'm going to end up dividing everything by 4. Well, you know that's going to create you a fraction. If I divide everything, if I isolate y, I'm going to have to divide everything by -3, and you know that's going to create you those fractions. So try to get into the habit of looking ahead, because it's going to make a really nice equation for you if you can isolate at first, make the good decision in the beginning to isolate the best variable. So take a minute and kind of think over that we've looked at all the possibilities here, and we've chosen to isolate this y because it gives us the nicest result to sub into the next equation. So I'm going to show you what I mean. So let's go back to our actual note here. So here's our example. And step 1 says to isolate one of the variables in one of the equations, and we've seen y, but now we're going to actually go into number 1, and I'm going to do it here again. So -3y is equal to 9 minus 6x, divide by -3. Just redoing the work that we just saw. Y is equal to -3, -3 plus 2x. So y is equal to -3 plus 2x is just equation number 1. It's just this first line rearranged with y isolated. Okay, so now what I'm going to do is I'm going to take that expression for y and I'm going to substitute it into y in the second equation. So we're right back on track with what we want to do with substitution. So I'm going to write out equation number 2 again. It's just 4x minus 3y is equal to 5. All I did was write out equation number 2. And then the next step of substitution tells me to take what I know y is equal to and sub it right in the spot for y. So let's go ahead and do that. Not going to write y. I'm going to substitute in what I know y is equal to. And I have to remember, don't forget, we have to do it in brackets because it's that y was being multiplied by the -3, and the expression for y is also going to be multiplied by that -3. So this was a y in here, and now it's what y is equal to. So we subbed it in. And now we have one equation with one unknown. We have 4x. We're going to have to expand in that 3, distribute it in, and we get plus 9 minus 6x, and that's equal to 5. I have 4x, I have -6x, so I have -2x's. This 9 is going to have to be subtracted from both sides. -2x is equal to -4. Divide everybody through by -2. And we get that x is equal to +2. Oops, I need to see that. So x is equal to +2. And after all of that, we are halfway done. X is equal to 2, and we now need to find out what y coordinate goes with that. So we are going to sub x is equal to 2 into one of the equations. Doesn't matter which one. I'm going to sub it into this one because it already has y isolated. So I'm going to sub it into our rearranged number 1, which is y is equal to -3 plus 2x. Y is equal to -3 plus 2 times, now I know what x is, it's 2. -3 plus 4, y is equal to 1. 1 is the y, 2 was the x, and 2 and 1 together is the coordinate that creates the point of intersection that would come if we were to graph these two lines. We'd be able to read that point of intersection right off. Today we realize that we don't need to graph the two lines. We can use substitution as our algebraic method to find that point of intersection that is still that spot where those two lines actually meet. So go through the steps as again today. Try this on your own. It does start to get pretty easy once we start to kind of see the pattern with it. But remember what your goal is. It says it right in its name, substitution. You want to get one of the variables isolated so that you can take that and substitute it right in the other equation for that same variable, so that you're just left with one equation you can solve nicely and carry it through, always keeping in mind that it's this point of intersection that you're looking for.